All right, Internet, what is going on? It's been a while. So today what I wanted to talk you through is a potential future that we could see that's not too far off, maybe a year, 2 years, where we have code that can heal itself. And I want to talk you through some of the research in the products that I've seen today in the last year that allow people to automatically patch their vulnerabilities with LLMs. Pretty excited about this because I think it's a really cool thing for defenders to have and a benefit for developers to experience so they can save time and not having to always patch a bunch of vulnerabilities that aren't necessarily conducive to either interest or innovation, and also getting better products out in the market. So with that being said, I wanted to walk you through some of the stuff that I've seen in the last couple of weeks that's been published in the last year. The first one here I want to talk through, or I won't talk through in all of these detail, but just note that you can see on the timeline here, this has all happened within 9 months, and there's been a really tight kind of amalgamation of things being published in this little cluster here as well. So the first one here with Google, this one and this one, these are all research. So these are papers that have been published, but the good thing about these papers, because oftentimes with papers, it's really hard to implement that in production, but the good thing is that the things they're doing here are not too technical. They're not too hard to do. And reason being is that what they're using, some are fine-tuning models, which is a bit more sophisticated, but most of the time it's using high-quality context that you're feeding into a model, as well as some fancy prompt engineering. If you can orchestrate that with LangChain, you then can create your kind of own in-house automated patcher, which is quite cool. So these are the 3 papers, and then here, these 3 here are actually products and or benchmarks. So Microsoft, I think actually 2 or 3 days ago, made this generally available for everybody. It's been in beta for a while, but this is a something that's attached to GitHub. So you can switch this feature on, and it allows you to automatically patch vulnerabilities with their auto fixer. And it gives you patch suggestions, and then you can either accept or reject the diff that they've committed. This here is a benchmark, so this is actually comparing different patchers, LLM patchers together, seeing which one's the highest quality. Also, this company called Patched or Patcher, something like that, they offer a framework that you can use to automatically patch vulnerabilities as well. Last one is from SimGrip. So SimGrip actually has an assistant called, I think it's called Assistant or Assistants, and they allow you to accept or reject automatic patches they send you based off of the SimGrep detections that come out from their static analysis tools. There's a lot of stuff out there. This is just a few things that I've seen recently, and hopefully from this video and from potentially the blog post that I put out, you'll see the possibility of doing this and the lack of complexity, which then brings it down to the masses to play with. All right, so this next slide is basically walking through a general flow of a Frankenstein version of all of these things I've consumed. So each and every one of them do something slightly different, but they have a lot of commonalities amongst them. So I'll first walk you through a high-level view of what a general flow looks like. I'll then walk you through a very specific flow for LLMPatch over here, because they're the most transparent with their paper and they give you the most detail. And then after the high-level flow of LLMPatch, I'll then go into some specific nuances around what they do and maybe why they do it and the benefits associated. So with that said, first flow. Most of them all start with the same traditional stuff that we have today. So we have developers that are writing code. When they have that code written, they then push that to some form of CI/CD pipeline. When they push that to the pipeline, that pipeline should hopefully have some scanners inside of it. So those could be static analysis, they could be runtime, it could be a series of different types of scanners, so dynamic, etc. Most of them in these papers, they focus on static analysis, but you can do this in different ways. After you've scanned the code, next you're going to send that vulnerable code into an LLM. But before you do that, oftentimes what people are doing is they're not just sending the vulnerable code, because if you just send the vulnerable code, it's usually overwhelming for the model, and the model is less accurate when it tries to create a patch. So what they're doing here is they're not just sending the code, but they're sending the code, and then they're sending maybe the line that's vulnerable. Maybe they'll even send a specific SWE ID with the vulnerability and some other context that I'll explain later. And they'll then attach all this stuff together. They'll then push that to the model. The model then thinks through what the fix could be. There's different ways of how you can do this. Each of them approach it differently, but just note that the LLM's thinking about how it can fix it. Once it's thought about it, it's actually going to spit out multiple patches. Oftentimes, they probably send maybe 3, I've seen 3 to 8 patches being created. Usually the sweet spot's between like 4 and 5. It creates multiple patches. Once it's done that, it does testing. So I think Google does this the best, where they actually test every single one of the patches in an automated fashion. They see if it's actually passing the specific unit tests they have for that code that they've patched. After that, they then send this off to another LLM. So this is actually considered an LLM as a judge. And this is what I think most of them do. And this just saves a lot of time. And it's another automated way of getting a high quality response. And there's a lot of really good research out there. I think I'm going to write a blog post on this, so I'll link it in there. But just note that there are, I think Eugene, I forgot his last name, but Eugene has written a good blog post on LLM as a judge, covering all the different research papers that have covered the topic. There's a lot of YouTube videos out there on LLM as a judge. But basically what you're using is an LLM to validate if something is both valid and or correct. So each one of them have different definitions of what correct is. And I'll give you some specifics on LLMPatch's perspective, but they're going to determine if the patch that's come through, is it correct or not. If it is correct, then we'll go to the next step, which is aggregating all of these into one. So they'll probably rank prioritize the patches to see which one is either the most correct based off of voting or something else. And then once they figure that out, they'll send it off to a developer. So this goes back into the human. We've automated most of this process. So from this step to this step is all automated. And then right here is where a human comes into play. The human's going to assess the patch. Once they've assessed it and they are happy with it, they'll then accept or reject. If they accept it, that then gets pushed to production. And this entire process has actually saved quite a bit of money. I've done some really bad back of the napkin math for Google, because they state kind of how much time is saved, how many vulnerabilities they sometimes see per month, etc. And then on average, per year, they're probably saving between $200,000 and $1 million a year based off of the number of vulnerabilities they're seeing, how many they're being patched automatically, etc. So that number is probably way off. It's probably a lot higher based off the number of vulnerabilities they see and how much engineers are paid at Google. But just generally, you're saving a decent amount of money with this new system. That's the overall flow. Now, I want to go into the details of what it looks like for LLMPatch. So LLMPatch starts the same way. They have code that goes in, vulnerability scanning. It is slightly different where they've just used a database of vulnerabilities. So instead of actually starting from scratch, they started with a database, 2 databases actually. There's roughly, I think, 13,000 vulnerabilities in there. They got it down to 300 that met their criteria. From those 300, they had separated it. So they have 200 in the training data set. And it's not really a training data set, it's more of examples. And then they have 100 for a test data set. This is where they're validating if LLMPatch actually works or not. So we'll talk more about what this is in a second, but just note that that's how they break it up. Once we've done that, we're going to send it off to this tool called Yorn. So Yorn is it's a kind of a graph creator. So it creates a specific graph called a program dependency graph. And I'll explain in more detail what that is. But just note what's happening here is, but we're going to run this through a graph because we want to focus the LLM's attention. Oftentimes, like I said, if we give it all the code, it's going to not know what to do. But if we give it specific lines of code that are all dependent amongst each other, and they're all connected to the final vulnerability that's the weakness, that's going to narrow the LLM's attention and focus on what actually matters. So I'll explain what that looks like and why we're doing it, but just note that's what's happening. Then we package all this up. So we take the graph, we take the vulnerability, the line of code, etc. We send that off to the model. That model then thinks through the root cause. So what is the root cause of this vulnerability associated to the code? Once it thinks through the root cause, it's then going to actually take the training data set that I mentioned previously. And like I said, I'm going to talk about all this in more detail in the future slide. But just note, we're going to take that training data set that has a bunch of examples that has root causes. And we're going to compare. So we're going to take root cause 1, we're going to compare it to the other root cause. We're going to iterate through all of these to figure out exactly which root causes are the most similar to the root cause that I found as my LLM. Once I've done that, I'm then going to take that information and I'm going to create a bunch of patches. I will create 5 patches in this specific use case. Those 5 patches are then validated by a series of models. So I think they have 4 state-of-the-art models when they wrote the paper. So it's Gemini, Claude, OpenAI, a bunch of others. They check for both validity and correctness. After they've done that, they choose the best patch, and they then send this off to the developer then to either accept or reject based off of what production kind of setup they have for their code. That's the general overview of what's happening here. Now, the next slide, I want to talk you through in more detail some of these nuances associated to what they're doing and the benefits of doing it. And the reason I wanted to talk about LLMPatch is, first, they're transparent, but second off, in this specific paper, they were able to patch 7 0 days of 11. And no other paper or production app that I've seen has been able to actually patch 0 days. Reason being is most of them are trained on existing vulnerabilities, so when they see something new, they kind of don't necessarily always successfully create a patch. But with LLMPatch, they've done a really good job. 7 out of 11 is pretty good, especially when they're only using GPT-4. So it's somewhat of an older model, GPT-4. Now we have GPT-4o, we have Claude 3.5 Sonnet, we have a bunch of the Llamas series, we have all kinds of new models that are better than that. So the effectiveness is likely increasing. And another thing with this specific approach that they're taking is they can patch a bunch of different languages. So they're not just looking at C or Java or something else, but the way they structure this is they can apply this to many different languages as well. So a few reasons as to why I'm focusing on this specific paper. Next. All right, so here I want to do is some more detail. So I've already talked through this a bit. I've already explained that we have code that's going to go through a commit process. It's going to be scanned, and that's going to be sent to something else. This is more interesting. So this is the dependency graph they're creating. This is one of the nuanced, specific things they've done that's unique for their paper. Where the way this works, so a program dependency graph, what is it? It's basically when you look at code, you figure out what are the dominoes connected to the primary domino. And what I mean by that, so down here, we have in red the vulnerable line of code. This is the code that's vulnerable that we've gotten out of our static analysis tool. But the thing is here, oftentimes with code that's vulnerable, it's not just in this line, but usually it's connected to previous lines that the vulnerability is held. And the way we can look at that is by assessing the data dependencies, so the data flow and the control flow dependencies associated to this line. So in here you can see the connections between. So we're saying, okay, this one here is connected, this is a data input. And over here you can see this is a data input, this is a data input, this is a control flow. So when this thing breaks, it comes here. And there's this if statement logic breaks, it comes here. So there's execution connection and data connection. And what they're doing with this is they're actually taking the lines of code, not giving everything to it, because remember, we want to focus the attention of the LLM. We don't want to look at everything. We want to focus its attention. And by doing so, we're actually going to take only these lines of code. So we're going to take the lines that have the arrows associated to it. We're going to package that up and send that off to the context. When we package that up and send it to the context, the quality of responses are much higher. Because in this paper, they actually did some A/B testing. They said, okay, if I switch off the graph, how does it perform? If I switch off the semantic or dynamic prompting, which is another thing they do, how does it perform? And they basically A/B test the approach that they have to see what's the weighting of importance around quality for each of these responses. And many of the net new things they've done has a drastic impact on how high quality the patch is from the LLM. This is one of the things that matter, is we're focusing their attention on what truly matters, the interconnection between the lines of code. So that is the dependency graph. So once we've done this, we want to package up the dependency information down here and the location of the code. We want to package that up with the SWE ID from the vulnerability that was probably from the static analysis tool. And we want to then have the vulnerable code itself and location of it. So we have the dependency graph, associated lines, vulnerable code, location, and SWE ID. Send that off to the LLM. The LLM in this step is then going to think through, okay, with all the information you provided me, what is the root cause? Why is this happening? And the way we do this is the prompt that they have in the paper. So they give it, like I said, the code, they give it to the SWE ID, they give the line of code, they give the graph, etc. And they then ask, what's the root cause? If it's unable to figure out what the root cause is, what's going to happen next is it's going to then ask another LLM, can you please provide a summary of the function? So then the LLM sends back the summary function, so the function that they're looking at for the vulnerability, and it then tries again. That usually solves the issue if it doesn't know necessarily how to do it initially. Once we've done that, this is where we start doing the comparisons with the previous examples we have from a training data set. So in this database, I remember I said there was 200 examples, and these examples have a bunch of information inside of them. So it has everything that I've just mentioned previously. So it has it has a SWE ID, it has the location of the code, it has the vulnerability, it has the vulnerable code, the SWE ID is a vulnerability, and then a bunch of other things in here, right? So these examples contain this information. Oh, and most importantly, I forgot to mention, it has the root cause. So let's underline that and make it unreadable. And the reason the root cause is important is what we're going to do here, as you can see in the prompt, is we're going to say, okay, can you please find similar root causes associated to the root cause you came up with? And what the response is just basically say yes, no. So it's going to go through all the examples and compare all the root causes. And it's going to ask, okay, is this similar or not, based off of different types of criteria you've given it. If it's similar, if it's yes, then they're going to take that and they're going to cache it. So they have one over here. And they're going to take another one, and they do two. They're going to go up to 8. So 8 is as high as they'll go. Reason being is probably they don't want to overload the context, and they want to focus their attention. But also this might be like a sweet spot that they found that there might be diminishing returns associated to the quality of the outputs. So that's our process with comparing the examples. Once we've done that, then it's time to generate the patches. So we want to generate the 5 patches, and I'm not sure why this says examples. You can just ignore that, internet. This should be patches. All right. And what this is kind of a bigger prompt, because this is basically the prompt of all prompts that we're going to feed into the model to create the patches. So in this prompt, we have all the examples. So we have up to 8, like I said in the past. So this could be example 1, example 2, 3, 4, 5, 6, and then we have a break here, and then we go into the ask. So this is the context prior, this is the ask. So the ask has, okay, given the follow line of code, we've given it the code, the SWE ID, like I said last time, the location of the line of code, the dependency graph, all that stuff. And then we're going to actually instruct it to give a structured response. So we're asking it for it to give us a structured response. We're actually going to pre-fill some information. It's kind of a form of priming for the model. So we're priming the model saying, here's information you've already gotten and you've already thought through, and this will help you think through the patch. And the two things we're going to fill are steps 1 and 2. So we've already thought through the root cause in the previous step here. So we're actually going to pre-fill that here. We're going to give it a root cause. Here we're actually going to propose a fixed strategy which is associated to the root cause. So when they have the root cause, when that pops out, there's also a fixed strategy associated. So we're going to put that in here as well. So this is our pre-filled area. And then we're going to ask it, okay, now come up with 5 patch suggestions. And that's the overall arching prompt they feed it and the goal here. When they come out with the 5 patches, this is where we start to validate. So like I said previously, we have 4 different models that are validating every single patch. And if one of these models says yes, then that then gets pushed off to the next phase. And as you can see in the prompt, it's stating, can you validate if there's this patch is vulnerable, etc. I think there's a definition, not maybe mentioned here, but somewhere in the prompt that's not in the paper, but maybe they forgot to share, that when they look at this, they look at validity and correctness. So I think validity is associated to does the code still function, and then correctness is it actually fixing the vulnerability, and is it solving the problem? Each one of these will check that, and like I said, if one says gives it a yes, then it moves on to the next phase. And when we go to the next phase, that's when we push it off to the developer to review, and they then decide, okay, based off of the patches that have gotten yeses, I figure out which of these is the best, and I'll push it off to the front. And that's the flow. Those are the nuances. And some of the main takeaways I've taken from this paper and a series of other products, the things that matter most when it comes to creating these systems. So first and foremost is context. Like I said previously, we need to ensure that even though the memory for these models is quite big and they can take a lot of context in the context window, we want to focus our attention so we get really high quality outputs. So to do that, in this specific case, they use dependency graphs, they use SWE IDs, they use root cause analysis, they had a structured format for the prompt and a structured output from the model, and they kind of even primed it with some pre-filled information, and they're really focusing and honing the information on what matters, and they do this in a dynamic fashion. So they mentioned there's dynamic prompting in here, which actually I mentioned up there, so I'll talk about that in a second, but just note the context we're fitting in here needs to be narrowly focused and isn't too distracting for the model. Next is traditional tools. So traditional tools still need to be used today. So we're using static analysis for all these systems. We're using dependency graphs from Yorn and other things. So all these different tools, unit tests from Google, etc. So we need to use all these tools to enable and amplify the abilities of these LLMs for today. I don't know what's going to happen in the future, but just note today, this helps the quality of the output improve. And the final one is dynamic prompting. So as I mentioned previously, dynamic prompting in this paper specifically, the entire prompt structure, the big one that I shared with you that had the examples and all the other stuff, that's dynamically added over time. So no human is involved, it's completely automated based off of the comparisons of the root cause and a bunch of other things. And that's what they call dynamic prompting, because we're not necessarily giving it a generic prompt. We're giving it a very specific prompt to its vulnerability that it's been shown and the associated root cause and everything else. So it's somewhat dynamic in nature. So the model is actually looking at what matters instead of a generic template that we're sending to it. With that being said, that's the presentation. And like I said, this is an exciting future where we could actually have code that heals itself. And that would save a lot of money, save a lot of time, and also save a lot of pain that people run into when they have vulnerable systems and hackers get into them. So with that being said, I hope this is informative, entertaining, and internet. I'll see you next time.